charged. Are there questions now or?
Thank you. All right. If we can, if Willie will sit down, but Willie is ignoring me. Oh my goodness, it's impossible. Herding cats is easier. All right. Thank you, everybody. Thanks for being here. I hope you had a great night last night. I think yesterday was a great conference. So a great start to the conference. So we're going to start with the pitch presentations this morning. And if you will start, oh, hold on. Yeah, if you put the list up, if you can stand in a well-organized stripe. Oops, something's not right. You don't have. Oh, we didn't have the list. Oh, well, but then don't worry about it. Just put the presentations up. So if your name is on the presentation for a presentation, please come and stand in a well-organized straight stripe here on the left-hand side as usual. So the first one is Lisa, then we have Pascal, then we have Andrea, then we have Letitia, then we have Jezri. First we have Angela. Oh, sorry. First we have Angela. All right. There we go. Sorry about that.
Morning, everyone. I'm Angela Martin. I work at Natural England. Can you hear me? Okay. Yeah, I work at Natural England. I'm Angela Martin. I work with Jacob Bentley, and we are using EWE to provide evidence to decision makers. And this slide just shows some of the impact that our work has had using EWE. So recently, Natural England won an award from the Blue Marine Foundation for its evidence that led to the sand eel closure in English waters. We also actively engage with the ISIS science community, and we can use EWE models for evidence only if they have transparency on data sources and decisions made during the development and balancing of the model, so that we can explain the caveats and the uncertainties to policymakers that are associated with the evidence. Thank you.
Thanks, Angela. And then I think we have Lisa. Yes.
Zoomed in, yeah. Yeah. Hello, everybody, and welcome to my office. My name is Lisa, and I work at ILVO, which is also located within this building. I work on the EcoScope project, where we are responsible for the EWE model of the Southern North Sea. So our model is based on the year 1991. It contains 45 functional groups, 9 fleet groups, and is mainly focused on plaice and sole, because these are really important species for Belgian fisheries. So currently our model is still in the calibration process of the EcoSim model, but we plan on continuing to the ecospace components and on testing scenarios related to fishing efforts and climate change. So if you have any suggestions or any feedback, please feel free to come and visit me at my poster and have a chat with me. Yeah, thank you very much.
Thanks, Lisa. Next, Pascal.
Sorry. Yeah. Sit now. Yeah, now here. Okay. Sorry for the first two. Just starting.
But
Leave it.
yeah, don't touch it. You're not allowed to touch it.
Yeah, if it's too high quality.
It worked so well yesterday.
Okay.
There we go.
Thank you. Good morning. I'm Pasquale Ricci from University of Bari in Italy, and this study describes a method to assess the importance of functional groups in the benthic pelagic coupling process, which is an important process for the exchange and of energy and the recycling of matter in the ecosystem. And in this method, we exploit the Ecopath consumption matrix, and after the classification of functional groups according their ecological domains, we develop an index to assess as the sum of downward and upward consumption flow of each functional groups, their importance in this exchanges process. And the results stress that the demersal and bentopelagic species in the food web and in this process are important to upward consumption flow and to sustain this exchange. Thank you.
Thank you. Excellent timing. Andrea?
Hi.
I'm Andrea Kaplan, and I'm a first-year PhD candidate at ICM in Barcelona. And in my poster, you'll see the study we're conducting on the effect of marine heatwave characteristics on the Western Mediterranean marine ecosystem. So first, we ran a marine heatwave detection on a temperature time series at 3 different depths, and from 1993 to 2022. And the idea is to then drive an ecospace model using these time series and compare them to a simulation with no marine heat waves, and see the effects that they have in the food web. It's a work in progress for now. But if you want to find out more, we have some preliminary results on the heat wave detection that are on the poster and some details on the methodology that we're planning to use. So feel free to come check it out and talk with me later.
Thank you. Letitia?
Hi, everyone. My name is Letícia. I'm a PhD student from University of São Paulo in Brazil. We are modeling a complex fishing fleets interactions with ecosystem components in the South Brazil large marine ecosystem up to 100-meter depth. Our model has a total of 38 compartments.
Speak
Sorry.
louder.
Our component has a total of 38 compartments and 10 fishing fleets. And we present the ecosystem state in 2022. Our main result was the LME greatest biomass removal ratio from the total of the 10 fishing fleets. And the 29 tropical groups come from the pelagic fleets, although the major impact is from the trout fishing. And we calculated the biomass ratio for all the fleets. So if you want to know more about it, you can come to my poster and I will be happy to explain more. Thank you.
Thank you. Jayshree?
Goedemorgen mensen. My name is Jayshree and I'm a research scientist at Middlesex University. And I'm working with Kieran Tate. Okay. From Surge, as well as Dr. Omar Siam from Middlesex University. And we are looking at modeling the oil dispersion and its impact on the Mauritian ecosystem. For those of you who are not aware where Mauritius is based, it's based on the right side of Madagascar. It's a small island that has been recently impacted by an oil spill called the Wakashu, which happened in 2020.
basically, we are in a preliminary stage of our work, 6 months. We have created a eco web for Mauritius based on data extracted from the sea project. And we have currently modeled oil spill concentration using WebNome and PyNome, and we are hoping to improve our data. This is some of the impacts that have been seen, and we're hoping to merge the data to look at oil spill impacts on shoreline as well as depth. Thank you.
That's okay. Christina?
Hello, everyone. My name is Christina Charette. I'm a PhD candidate at the University of Quebec in Montreal, and I work at the River Institute in Cornwall, Ontario. So we're trying to build the first model of a freshwater portion of the St. Lawrence River from Ontario all the way to Montreal. And I'm looking for any tips, any feedback to how to model the influence of invasive species such as the rango bee and the zebra mussel and contaminant flow in this large fluvial ecosystem. So please come chat with me, because like you see, it's for me as a first person using Ecopath, it's pretty complicated in my head right now. So let's hope you can help me out. Thank you.
Thank you very much. I think Maria?
Yeah, it's good. Yeah. So, hello everyone. My name is Maria Castro. I'm doing my PhD at the Institute of Marine Science in Barcelona and the University of Barcelona. And here is our work about using the eco-space model of the Western Mediterranean model to simulate what will be the effect of banning bottom trawling within Natura 2000 sites in the Western Mediterranean. And why banning bottom trawling within Natura 2000 sites is because it's a proposal of the European Commission by 2024 in Europe. And then we will also test what will happen under different climate change scenarios, and we will be using EcoSpace. And please feel free to come to my poster, chat to me, and you have any feedback, any comment. It's our work ongoing. We have still to define specific objectives, what we want to look at, biodiversity indicators, ecosystem indicators, and everything. So please feel free to come and chat, and thanks a lot.
Thank you very much. I think Cecilia is next.
Hi, my name is Cecilia Huvel. My poster is based in Lake Erie. We've been doing some ecopath modeling there, looking at spatial and temporal variation of food web structure and trophic transfer efficiency. So we've done the ecopath portion we've done the ecopath portion of our modeling at this point, and we're moving into time series ecosim and eventually ecospace. So why Lake Erie? Well, it's one of the largest freshwater lakes within the world. Also supports one of the largest freshwater commercial fisheries in the world, and is kind of the poster child for environmental issues, environmental stressors in North America. So makes a really great model system.
Thank you. Laurie, and now Rosen. Sorry, you're going to have to pronounce your name because I think I did it wrong.
Okay, so my name is Roisin and from AFBI, and my project is looking at the impacts of the discard ban in the Irish Sea. So we've been collecting diet analysis information and fisheries data to create a model to look at different discarding scenarios, but it's still in progress. So any advice or help would be appreciated because it's my first time using Ecopath. Thank you.
Thank you very much. I know that way it's better. Laurie? Oh, yeah. Yeah, it's safer to go down there, people, because there's a step there. There's no step here.
Good morning, everyone. My name is Laurie Michaud, and I am engineer in the University of Normandy. I'm modeling the impact of offshore wind farm in the English Channel on the food webs. And in fact, the offshore wind farm impact ecosystem, their function, then stabilization. That's why we have to know how does work. And in our project, we use two software packages to build the food webs. They are linear inverse model and Ecopath and its extensions. Both there are drawbacks and advantages, but they could be combined together to build but to improve the construction of the food web model. So to understand why and how the complementary could be implemented, I invite you to look at our posted at our methodology and ask me some questions. Thank you.
Thank you very much. Janis?
Hello, everyone. My name is Jānis Grudls. I'm from Institute, in short, BIOR from Latvia. Unlike most Ecopath models, we try to apply this method to lake ecosystem. And I think we had a very great opportunity within the project to point out from the very beginning what kind of data we need to build a successful model, a dream of modeler, right? And so we carried out intensive lake research for a period over 2 years and did the research on almost every trophic levels and made a static Ecopath model of 23 functional groups. And this model is supposed to support future management decisions, and continued monitoring is going to lead to dynamic ecosystem model in the future. Hope so. Thank you.
Santiago?
Hello, everyone. I'm going to talk to you today about this side project that we've been doing with a bunch of NGOs in Peru, where we've been repeating a process that we did in 2009 to construct a full value chain for the Peruvian ecosystem. And we've used the same groups, we've interviewed the same people pretty much, and overall the models have not changed quite that much. The years were quite similar, 2009 and 2018 in terms of environment and catch, but in between we signed free trade agreements with over 80% of the economy. We had a catch system installed in our largest fishing fleet, and we had a fully unregulated small-scale fishery just explode. So one thing that we're seeing is a lot of non-stationarity in value chain parameters that are assumed to be constant. And that is quite an interesting thing and a challenge for future modeling with value chains and ecosim. And at the same time, we've seen, we're able to track really well cost structures for the different fleets. And we've detected a 250% increase in fuel costs for the small scale fleet. There's lots to talk here. So please find me. Cheers.
Thank you. Alonso?
Hello, I'm Alonso del Solar from Peru. Our work deals with a marine port that has been built in Peru for a natural gas plant. So we have it before in 2006, after in 2009. Luckily, there's a nice monitoring program, which is a first, let's say, because usually we use Ecopath models after the fact, no? So in this case, we have nice data starting after the port was built. But now we were at this stage. We want to build an ecosim model also, an ecospace model. I know some other people have experiences in other places with large marine structures. This first model it's a bit flimsy. We need to still probably adjust for fish and others, but we'd love to hear what you have to say about this, no? Yeah, basically that's it. Thank you very much.
Thank you, Alonso. Sergio?
Morning, everybody. My name is Sergio Neira. I come from Chile. I'm giving this presentation on behalf of Ana Arriaga. She's a PhD student under my supervision. And unfortunately, she couldn't make it, but we have been using EWE models to evaluate the role of sea lions as predators and their role in the collapse and lack of recovery of main Chilean fisheries. So the main result is that at least our verdict is that they are not guilty. And you're welcome to visit Chile and ask Anna for details. But if you can do it, I'll be around, so you can. I'll be happy to talk with you about our models and results. Thank you.
Thank you very much, Igor. Igor? Who gets the prize for giving his slide the latest?
So, hello everyone, I'm Igor Celic from the National Institute of Oceanography and Geophysics in Italy. And so me and Simone were approached by the WWF to assess the impact of certain management scenarios for a small-scale fishery, the reduction of effort, the reduction of area, change of fishing gear, and so on. And so we decided to approach it through a spatial model. And so from a perspective from somebody that was on the fishing vessels, I was expecting that some measures would work in a nice way, but actually the full web model, and this is the nice thing about it, there's completely different things. So there is trade-offs continuously and no win-win situation. So if you wish, you can check at us and see how our spatial modeling worked. Thank you.
We don't seem to have Gabriel here, but Eyal,
Yep.
next.
Good morning, everyone. Eyal from IOLR. The more holes we are drilling in our sea, the more danger we're exposing our ecosystem to. But having said that, it's not enough. We need to find a way to quantify the effect of those drilling on the ecosystem. That's exactly what we did. It's not that. But it's not that, it's this one. It's not what they did. Anyway, that's exactly what we did. We find a way to use the ecospace model in order to quantify the effect of oil spill in our ecosystem. We run several scenarios. We have an interesting result, and mainly we develop a method. And if you want your model to be a count and you can think you can use the method in your ecosystem, you're more than welcome to approach me at the poster session, and maybe we'll use this method in your area. Thank you.
Sorry, that was the previous poster was yours, Samuel? Sorry, it was Eyal's fault for standing the wrong time in the line.
Oh, mine.
Actually,
Yeah.
no, it was my fault for not looking at the list. Sorry, Eyal.
All right, I'm not going to wait until the slide loads. I think it takes some time. Well, anyways, thank you for having me. My name is Samuel from the University of Gothenburg, where I recently started my PhD on modeling the effects of offshore wind farms on marine ecosystems. And offshore wind is a very hot, but still very understudied topic. And the knowledge on the long-term effects of such installations on marine ecosystems is limited. So in my work, I'll try to shed some light on exactly that by incorporating the main associated effects, namely the introduction of artificial hard substrate, underwater noise, fisheries exclusion, and barrier effects. So by having these big four in our model, we try to, I don't know, come closer to understanding how such installations alter the system and how species changes in species composition alter or propagate through the food web. And please don't let yourself be blown away by my neon green title. It's way too early for such ones. But yeah, anyways, I'll be happy to talk to you and come by. I would love to have your input and your views on the study design. Thank you.
Thank you, Xavier. One moment.
Yeah. Look at you, huh? Hello, I am here to present a group of researchers led by Marian Torres, in which we have used the Ecopath with Ecosim approach to assess the status of food webs within the Marine Strategy Framework Directive for the Iberian Peninsula. Through different meetings, the group was created. We established a standardized modeling approach.
and several indicators were selected. 3 of the models already developed of the Iberian Peninsula were used to assess the status of the food webs that were the Bay of Biscay, the Gulf of Alicante, and the southern Catalan Sea. And these results were presented to the Spanish ministry, and the results will be published soon. Thanks.
Thank you, Toby. And finally, Joanna.
Morning, my name is Joana Romero Henriques. I'm a postdoc at NIOS, and today together with Irun and other colleagues from NIOS, Sovon and Wageningen, we bring you the Wadden-Sea, the Dutch Wadden-Sea to be more precise. And for those who don't know, the Wadden-Sea has the largest intertidal system in the world. Because of this, it's partially exposed twice a day, and this makes modeling a bit complicated, but we'll get through it. But what we bring you today is just the current food web of the Wadden-Sea, but the idea then is to build up on it and to make projections using different climate scenarios and look to the future for the next 100 years. So without spoiling it too much, the Wadden-Sea is a mature ecosystem but presents low stability and resilience, and its future may be threatened in the face of global changes. So if you want to know more about it, come to see me or this nice old man and we'll tell you about it.
Thank you. And that is all the posters that we have. So I think that's it for the posters. The next session is session 3 on spatial modeling with EcoSpace, and Kim is going to lead on that.
Good morning, everyone. We're doing good on time, so I will try not to change that too much. You guys presenting, I'll hold up the 2-minute signs at 10 minutes. So you got 2 more minutes, still 12, 3 minutes for questions. This is the session on spatial modeling with EcoSpace. I am not doing the controls. Is that what I understand correctly? Okay. So as soon yeah, okay. So again, if you see the hats, those are student talks. So please vote for best student talk. Our first talk is a student talk by Samantha Grust, Spatialized Ecosystem Modeling of Marine Ecotourism in South Africa, a novel approach to representing the effects of provisioning for shark cage diving on the distributional response of top predators in an ecospace model. So Samantha, come on up.
Can everyone see me? I know I'm not the tallest person and hear me. Oh, sorry. All right. Very quickly before I get started, I just want to apologize in advance if I seem a bit frazzled. I got some bad news last night about a friend battling cancer, and I'm just really doing my best to hold it together right now. So just please bear with me. Yeah, thank you. All right. So today I'm going to be presenting part of my PhD. I'm actually at the very end of my PhD, about 2-3 weeks away from submitting my final revisions. Be looking at the influence of provisioning on for shark cage diving in South Africa and how we can represent that in EcoSpace. I'll just click. Aha. All right, so before I get started, what do I mean by provisioning? So for my study, provisioning is just attracting sharks to tourists for easy viewing, regardless of attractant method, whether it's using chum and bait, hand-fed shark dives, music or sound of certain frequencies, anything. So just attracting sharks for easy viewing. And within South Africa, the main form of provisioning is shark cage diving with great white sharks. And here we're going to be focusing on the southeast coast in the red box. In this area, is there a pointer? Yes. Okay, so shark cage diving has been happening here in Mossel Bay since the early 1990s, but that's not the focus of today. Today we're focusing here on Algoa Bay, where a new commercial shark cage diving operation was introduced in 2020 around the Bird Island group. This area also falls within the recently implemented Addo Marine Protected Area, part of South Africa's expanded MPA network in 2019. What's unique about this new operation is that they don't use food to provision the sharks. They rather say they use sound, music of certain frequencies with underwater speakers to attract the sharks. There's no peer-reviewed studies on the use of music in this way to attract sharks, but it's likely based off this company in Australia. He's been doing it for, I think, since 2015 or 16. And I don't know what kind of music they're using to attract the sharks. I know in Australia, they use rock music, specifically AC/DC, which is pretty cool. I like AC/DC, you know, good taste. So this new operation here runs seasonally from April through September. And in general, there's a lot of issues regarding the shark provisioning in general. So there's lack of standardization in provisioning practices and species-specific differences in life history and foraging traits. So because of that, the biological and ecological implications of this activity are unknown and difficult to quantify. So here, how can we represent this in ecospace? So for my model, a few conditions we wanted to consider is that since this operation does not use food to provision the sharks, we did not want to directly alter any food or consumption related parameters in the model to represent this activity. We also did not want to fully restrict all the great white sharks in the region to the provisioning site because in South Africa, great white sharks have known aggregation sites along the entire coast. So we know not the entire Southeast Coast population is going to be restricted there. We also do not want to influence the long-term broad-scale movements and home range of the sharks. And we did want to represent potential short-term local spatial shifts. There's no peer-reviewed studies really on the effects of provisioning in South Africa, but a couple studies in Australia have found that looking at cage diving operations, they found during active provisioning events that sharks were becoming more spatially concentrated within direct vicinity of the provisioning sites. But at the same time, there wasn't any long-term significant influence on their broad-scale movements of sharks in the same aggregation across their whole home range in the area. So how can we do this in ecospace? After a lot of brainstorming and a lot of discussions, we've decided we can use artificial habitats with a habitat suitability index to represent this activity. So we made artificial habitats for provisioning season and for non-provisioning season. And I'm going to quickly just kind of walk the red stripe, sorry, is the core provisioning area. So it's the direct vicinity around Bird Island where the operation is going to be happening. The spillover area is right around, so this is based on literature. I don't have too much time to get into it now, but having a spillover area. So we know that sharks occur, this Algoa Bay here is a known aggregation site of great white sharks. And we know sharks occur here all year round. And so we know not every shark in the area is going to be right in the core area. Sorry, my hands are a bit shaky at the moment. So we have a little spillover area. And then this green stripes here is the rest of Algoa Bay because, again, we know the sharks are occurring there. And it's not likely that every shark in this area is going to be attracted to the cage diving vessel. And the solid blue is going to be the same in both provisioning and non-provisioning season. And this is just everywhere else in the Southeast Coast grid where great white sharks are known to occur because there are already also known aggregations of white sharks here in Mossel Bay, Plettenberg Bay, and Jeffreys Bay as part of their known coastal migration or swimming patterns. So for non-provisioning season, the habitats are, so based on literature, there's studies that just looking at the general behavior of the white shark aggregation in Algoa Bay, I've noted that during these months, they have a higher inshore peak presence. But again, not every single shark in the aggregation is going to be in this inshore area. So this gray area is the rest of Algoa Bay where we know this aggregation occurs. And like I said above, this dark blue area is just the rest of the grid cells in the map where they're known to occur. So now how does this work in ecospace, setting it up? So I'm just going to talk through the idea, the theory of how we use habitat suitability and how it differed between the different habitats. Okay, so starting with provisioning seasons. So the red stripes, the core. So habitat suitability in ecospace ranges from 0 to 1, 0 being unsuitable, 1 being most suitable cell for that group. So the core area, the red stripes, has the highest suitability of 1. The spillover area then has a suitability value greater than 0, but less than that of the red stripes, less than that of the core area. Then the green stripes here, the rest of Algoa Bay then has suitability index also greater than 0, because we know that none of these cells are going to be completely unsuitable for great white sharks, but less than that of the spillover area. And then the dark blue, it's going to be same idea for both seasons. And that is going to be also a suitability index greater than 0, but less than that of the green stripes or the gray. When I say the gray, I refer to the gray here because that's going to be the same for both habitats. Similar idea for the non-provisioning season. And the orange stripes, the inshore area is going to have the highest suitability index because that's, we know in this time of year, this is their highest, most likely to occur. And the gray, similar, is going to have a habitat suitability also greater than 0, but less than that of the orange stripes. And as I mentioned before, the blue is going to have also habitat suitability greater than 0, but less than the gray or the green. And this was implemented in Ecospace through the spatial temporal framework, starting from 2020 onwards. So my model period starts from 2008 and then runs, and then 2020, these come in to represent the activity of provisioning, and then we run the model for an additional 25 years further, just to kind of, so we can see the influences of it. So sensitivity testing was performed on a whole range of habitat suitability values for each artificial habitat. I'm not going to get into the details of it now. I can chat about it after. It's just a lot of information. Additional sensitivity testing in the models performed on base dispersal rates and vulnerability to predation in bad habitats. It's in general. And these were the values chosen based on the sensitivity testing at this stage of the model. Ooh. I don't know what happened to the pointer, but that's okay. So I'm going to walk you through, so to show some of the, oh, there it is. Okay, so show some of the outputs. So we're looking at great white sharks, and we're looking at the model with the representation of provisioning compared to without representation of provisioning, and we're looking at the spatial shift in their concentration. And here in these maps, the very pale blue to white indicates no change in the spatial shift, meaning that the great white sharks are utilizing these areas to the same degree in a model with and without provisioning. And that's good. That's what we want. This is because these areas where you have these little to no changes are consistent with other known aggregation sites and their known coastal movement patterns. So essentially what we're saying is that they're using these areas to the same degree, and including the activity of provisioning in Algoa Bay is not driving all the sharks in the model area to Algoa Bay specifically, which is consistent with their known patterns. So I have a couple others. I'm going to skip over these for now. There's a couple other species that have known nursery areas, but I'm running out of time, so I just want to quickly go over some key findings rather. I apologize for all the text. I'm going to talk you guys through it. So we're seeing clear spatial shifts in some of the great white sharks, as well as some of the other top predators that are prey to great white sharks, and that also have known nursery grounds or breeding colonies on the southeast coast. However, in terms of total actual system biomass, both over the whole southeast coast grid and within Algoa Bay only, changed minimally between a model when we added provisioning and when we had no provisioning. So these minimal system changes, along with the evident spatial shift in concentration of great white sharks and other sharks in the area, or other predators in the area, suggest that this operation at this stage likely has not attracted new sharks to the area, which is great. That's not the goal of provisioning. It's like the goal of provisioning is rather to kind of bring sharks already known to occur in an area to different parts of the system for easy viewing. And that this operation is likely occurring at a small enough scale that it doesn't have such a long-term or significant influences on the whole Southeast Coast dynamics. Again, which is good. However, this is a very short foundational study, and a lot more research and refined parameterization and models are needed to confirm or to support my conclusions here. But mostly just about kind of representing this new activity spatially and with what's known about it. Yeah, thank you.
Samantha, we have something for questions.
I will ask if nobody else has one. But I don't know that there's an answer to the question I have. My question is at the moment you think that there's not going to be much of an impact, but what happens when you have change in behavior of the sharks?
Yes.
And how do you model that?
So that's part of the future refinement. So we're still figuring out how we would model that. Yeah. So I can't repeat the question again. Sorry, my brain's a bit frazzled.
Yeah.
The first part of the question.
The question is, what happens if you have a change in behavior, and how would you actually model that?
Yeah. So what would happen with the change in behavior? We're not exactly sure. Again, the only kind of studies that have looked done peer review studies on any cage diving sort of operation are a few studies in Australia. Yeah, and they've shown changes in behavior. They've shown slight conditioning. I don't know if that's the correct word to use, where they found, regardless of if provisioning was happening or not, there were a few sharks, for instance, were coming to the same site at the same time of day every day, regardless of if they were provisioning or not. So in that sense, there's that bit of conditioning. If we're talking about around Algoa Bay and Bird Island, so that happens right around a seal colony, the easternmost seal colony in South Africa. And great white sharks are naturally ambush predators. They stay below the surface and come up, get their prey, and go back down. You know, they can't be seen, camouflage. And one of my things I've always wondered is, like, if they're attracting sharks to the surface, again, regardless of if we're using food or not to attract the sharks, because the goal is still the same, bring them up to the surface for easy viewing. What does that mean for the seals? Are they being predated on more, or can they now see the sharks coming, and are they able to get onto land now? And that's one of the things we would like to, I'm not sure exactly yet how to model it. We need a lot more brainstorming and discussion, but that's kind of where I kind of want to go towards with looking at this kind of thing and how the change in behavior can affect the rest of the ecosystem. Yeah.
Congratulations by the presentation. Are you thinking to make a value chain for this activity?
We haven't talked about it or considered it much now, but it's definitely something to think about.
Yeah.
Thank
Maybe
you.
it could be interesting.
Yeah.
Yeah.
Now to talk to Lynn and Jerome and a few other people. Yeah. Thank you. Thank you.
Our next presentation is by Marie Lemarchand, Climate Change and Floating Wind Farm in the Bay of Biscay, an ecosystem approach on the local food web. Go ahead, Marie.
No, just do.
Sorry.
Good morning, everyone. My name is Marie. I'm a researcher.
Stand by the.
Oh, yes. Sorry. The voice.
Good morning, everyone. My name is Marie. I'm a researcher from France Énergie Marine, and I'm going to present the last result of my PhD work, which should be published soon. So the subject is the climate change of a floating wind farm in the Bay of Biscay, an ecosystem approach on the local food web. So as you all know, marine ecosystems are based on complex network linking biological components and environmental parameters in a dynamic balance. Marine coastal ecosystems are subject to numerous pressures affecting all the trophic groups, the main one being fishing activities and climate change. So offshore wind farms will be integrated into those complex ecosystems, but they have themselves their own impacts on all the trophic groups, which are the subject of numerous studies, such as electromagnetic frequencies, noise emission, aggregation of fishes, reef effect, and oceanographic changes. So the ecosystem approach enables an holistic studies on the cumulative effects on the entire food web. Our study area is the continental shelf of the Bay of Biscay in western France. It covers an area of 80,000 kilometers squares and is subject to numerous activities, such as fisheries, maritime transport, aggregate extraction, military and tourism activities. In an environmental point of view, it is composed of a wide variety of benthic habitat. It receives a large amount of nutrients, and so it makes a lot of spawning broods and feeding area. All these parameters explain the rich biodiversity that can be found in the Bay of Biscay. The offshore wind farm we are studying here is currently to be planned and will be located in the southern Brittany. It will cover an area of 45 kilometers squares and will be made of floating wind turbines installed at 82 meters depth. The sediment in this area is mainly sandy muddy. The food web we are studying in this has been created by LaSalle et al. In 2011 and has been modified in 17 and 22. It is composed of 44 trophic groups, ranging from phytoplankton to top predators. So today I will present 4 scenarios: a reference scenario with no climate change and no wind farm, a climate change scenario, a wind farm scenario, and a cumulative effect scenario with both climate change and wind farm. So now I will present the parameters that have been modified from the reference scenarios to model climate change parameters and wind farm parameters. In Ecopath, we have recalculated the P2B and Q2B of the fishes and cephalopods in order to take account of the rising in sea temperature forecast in the Bay of Biscay. This led to an increase of those parameters. We also added 8 groups of non-indigenous species listed in a previous study. For the wind farm scenarios, we added groups of fixed filter species, such as mussels, to represent the biofouling that will colonize the structure. In EcoSim, we forced the increase in biomass, in the biofouling biomass, in order to simulate the colonization of the structure by the biofouling. And finally, in EcoSpace, we use maps from niche modeling in order to force the future distribution of local and non-indigenous species. And for the wind farm scenarios, we use EcoSpace to position the wind farm as a marine protected area. This allows us to simulate a reserve effect via the restriction of fishing activities. And we also simulate an aggregating effect for the species who are looking for shelters under the floating structures via the foraging habitat usage. And of course, the cumulative effect scenarios integrates all of these parameters. So today I'm going to present the result of these scenarios on the biomass of 4 assemblages of trophic groups: demersal fishes, pelagic fishes, mammals, seabirds, and benthic invertebrates. In order to not be as a result, the biomass of biofouling is not integrated in the benthic invertebrates. For each of the trophic group assemblages, I present here the difference in biomass compared to the reference scenarios in the wind farm area. So all the values are in percentage. You can see on these figures, the left bar plot corresponds to the climate change scenario, the middle ones to the wind farm scenario, and the right one to the cumulative effect scenarios. So let's start with the climate change scenario. We can see an increase in the demersal and pelagic fishes biomass, which could be explained by the redistribution of the local species and the arrival of non-indigenous species. The slight decrease that can be seen in the mammals and seabirds biomass could be explained by the increase in trophic competition due to the arrival of piscivorous fishes and the high mobilities of mammals and seabirds. And the increase in benthic invertebrate biomass could be explained by the decrease in the predation pressure. I mean that the biomass of flatfishes is expected to decrease in this area with climate change. Also, this is not visible on these figures, and they are the main predators of benthic invertebrates. So it decreases the predation pressure and leads to an increase in the benthic invertebrate biomass. So now let's look at the wind farm scenarios. We see an increase in the demersal and pelagic fishes biomass that could be explained by the reef effect and the aggregation, so a high attractivity of the wind farm area. In the same way, the increase in the mammals and seabirds biomass can be explained by the attractivity of the wind farm due to the large amount of prey around the wind farm, around the wind turbine. And finally, we can see an increase in the benthic invertebrate biomass, but the strong predation pressure exerted by benthos feeders fishes leads to a general reduction in their biomass in the wind farm area. Finally, here are the results of the cumulative effect scenarios. We can see that the combination of the arrival of new species, the redistribution of local species, and the attractivity of the wind farm could lead to a large increase in the demersal and pelagic fishes biomass. However, we can see that there is a decrease in the mammals and seabirds and benthic invertebrates biomass. It appears that climate change could have greater effect than wind farm on the biomass of mammals and seabirds, but the wind farm could have greater effect than climate change on the benthic invertebrates biomass. So these results show that climate change is changing the local communities. This is the results that we have already highlighted in previous studies. On the other hand, the offshore wind farm could create a strong attraction in the area that could also change the current food web. And we saw that the cumulative effect of both climate change and wind farm is complex and is specific to each trophic groups. There are some limitations that have to be taken account in this result. Firstly, we didn't consider all the effects of offshore wind farm on the compartment, on the trophic compartment. For example, we didn't consider the avoidance of the wind farm area due to the electromagnetic frequencies and not emission. We also didn't change the fishing pressure. Also, although it will have to adapt to the arrival of new species and the multiplication of offshore wind farm. But these studies show the effectiveness of the ecosystem approach and trophic models in anticipating the effect of offshore wind farm in the context of climate change and on the entire food web, and to optimize the management scenarios. So here I show you only a few results of the studies, but we have also studied the effect on other trophic groups, on catches, and around the wind farm area. So if you want to see the result, feel free to get on my ResearchGate and wait for the result. Thank you for your attention.
Thank you, Marie. We have plenty of time for questions.
So I think that's a very interesting study. I think probably you need to give me more detail. Can you help me understand why the pelagic species actually increased? What is the connection between, what is the driving mechanism, I guess? And also, can you also help me understand how you define pelagic in marine ecosystem?
Sorry, can you repeat your question?
Oh, so well, maybe two questions. First, can you define, how do you define pelagic in marine ecosystem? And the second, what is the driver making the pelagic fish increase under the wind farm scenario?
Oh, okay. So firstly, we have the arrival of non-indigenous species with the increasing of sea temperature. Your first question was how I define.
What were the pelagics in the system?
Oh, it's a bit of tunas, mackerel, horse mackerel, sea bass, sharks. Yeah. I simulate in the wind farm the aggregating effect via the foraging usage. So I made the wind farm more sustainable for the species who will take shelters under the floating wind farm. So this explains the very high biomass that can be formed.
Two questions about time. First is, it seems the most notable finding is that 200% increase in pelagic species as noted. Was the creation of marine protected areas potentially the biggest driver of that?
Yeah.
Can you disentangle that?
Yeah, I forgot this
Okay.
in my answer. Yeah, of course, there is no fisheries activities in the marine protected area, so it also increased for the pelagic fishes.
And the second question I had is that those 9 non-indigenous species that were added to the system, are those specific species from like releases, or do those represent poleward expanding species due to climate change?
Represent what? Sorry, I didn't know.
Those 9 species, are those new species due to human releases, for instance, from ballast or aquariums, or are those poleward expanding species?
Trekking species coming
Okay.
from subtropical areas, especially Morocco.
Okay.
I modeled those species during my first year of PhD. So they are coming northward with the increasing of sea temperature. Yeah,
Cool.
it's not invasive species like coming from shipping, maritime transport. Yeah.
Thank you.
I didn't model this. Yeah, it's too complicated.
Time for another question. I don't understand.
Yeah.
Thank you for your presentation. I found quite interesting the fact that then non-considering the dislocation due to noise or for seabirds to the presence, you get an increase also for mammals. And I think it's just a brainstorming of how much careful we have to be when we are attracting species from the habitat and how much we are dislocating, because the trade-off is making the difference. And we know so little about these locations, species specific. So we have to be careful when we do it.
Yeah.
Just a consideration. Thank you.
Yeah, we are working on those questions in France Energy Marine. Yeah.
Hi, thank you for your presentation. I got a bit confused with the marine mammal trend that you presented. Can you go to the slide?
For climate change or wind farm?
Yeah, so the graph, this graph that you have. So for climate change, you have a decrease. Then for wind farms, you have an increase.
Yeah.
And then the cumulative impact, there's a decrease.
Yeah.
What was the explanation that you gave for this increase?
Yeah,
the
I think
decrease?
there is a high competition with the arrival of piscivorous fishes, and the high mobility of mammals and seabirds leads them to leave the area. But the large amount of prey with the wind farm makes them come in the area. And the cumulative effects show that, yeah, climate change appears to be greater, but I don't really understand why I got this result.
Okay, and you modeled mammals and seabirds together, is that it?
No, actually, this is an aggregation, but I modeled each trophic groups, and I made aggregation here to be simpler to show you. But if you want, we can talk about it because I have on my computer the
Thank you.
result of each groups.
Thank you.
Thanks to you.
Right. Our next presentation is another student presentation. So please think about voting. Ghassan Halawani, how to deal with a reduced spatial resolution in ecospace. Go ahead.
Just hello, everyone. Just to clarify, I'm not a student. I'm presenting the work of my master's degree student, Laura Cockbert. So today I will talk about how to deal with a reduced spatial resolution in ecospace. Okay. So for this, we used the ecospace model of the Bay of Seine in the English Channel in the north of France, developed for the period 2000-2015, and it represents 43 trophic groups. This model was already published in 2020 in order to explore the questions of the potential effects of fishery closure inside an offshore wind farm in the Bay of Seine. So the idea is that if we close the fishery inside an offshore wind farm, the offshore wind farm will act as a marine protected areas. So we expect an increase of the biomass inside the offshore wind farm, and a part of this biomass could be exported in the neighboring areas. So this is what you call the spillover effect. So in order to explore the spillover effect, we simulated two scenarios, a reference scenario and a fishery closure scenario inside the offshore wind farm, represented here by the white cells. And we can calculate a set of indicators, catch, biomass, and trophic level-based indicators. So here I'm showing rapidly some results of this analysis. So what we see here, we have the biomass indicators in the Bay of Seine with Ecospace. When it's red, it means a decrease of the biomass. And when it's blue, it's an increase of the biomass in comparison to the reference scenario. And we did this for the catch indicators. So the red area, it means that there is no catch inside the offshore wind farm. The trophic level-based indicators, but I will not go too much into the details because it's not the main questions for today. Our questions are how sensitive ecospace model of Bay of Seine to the spatial resolution and how to deal with a reduced spatial resolution. For that, we developed 6 ecospace models. They differ only by the spatial resolution. So here on the left, we have the spatial resolutions of the original model, the published one in 2020. So the size of the cell grid is 0.015 degree. And then we multiplied this size by 2, 3, 4, 5, and 6. So on the right, we have the ecospace model with the lowest spatial resolutions. So here what you are seeing is the size of the cell grid at the right scale. And then here in the slide, we have the different ecospace base maps. So on the top left, we have the base map of the original model. So as you see here, we can see clearly the different the details of the habitats, the fishing areas, and also in blue we have the offshore wind farms. And in the bottom right, we have the lowest spatial resolutions that we tested. So we see clearly that we lost a lot of details, and the offshore wind farms here, it's represented only by just one cell in blue. Sorry. So now I'm showing rapidly some results. We try to compare the results from the original paper and with the different spatial resolutions. So here we have the catch indicators when we stop fishing inside the offshore wind farms. So when blue, it means slight increase of fishing around the offshore wind farms. And when we decrease a little bit the resolution, so here we have the 0.03 spatial grid. Let's decrease a little bit more. Here we have 0.06, 0.07, 75 degree. And in this one, we have the lowest spatial resolution. So we can see clearly the impact of decreasing the resolutions. And in order to explore in details the impact of this decrease, we try to see what's happening in different regions. Inside the offshore wind farm, in the buffer zone represented by the yellow areas, and at the scale of the Bay of Seine. Then we summarize the results in this kind of plots. So here you have the percentage of change in comparison to the reference scenario. So in the y-axis, we have the different spatial resolutions. And here I'm giving example of the total biomass. And we try to see what's happening inside the offshore wind farms, represented by the diamonds, and inside the Bay of Seine with the solid circles, and in the buffer zone, the square, in the square. Yeah. So we did this for the trophic level based indicators, catch indicators, and biomass indicators. So the first result, we found that the model is sensitive to the spatial resolution. When we see here, we see that for almost all indicators, we have a clear trend. When we decrease the spatial resolutions, we have a bigger difference between the original model and the tested model, as you see here for 0.09, for example. Then we found also that the model sensitivity to the spatial resolution depend on the indicators. In fact, all the indicators, they don't have the same response to a decrease of the spatial resolutions. Some of them are very sensitive, like catch indicators. The change that we observed is up to 30% if we compare the original model to the, for example, the lowest spatial resolution model 0.09. And we have also biomass indicators which seem very sensitive, but less than catch indicators. The observed change, it's up to 20%. However, for the trophic level indicators, they seem not very sensitive. They look, let's say, robust. The observed change is about less than 6%. And finally, we found that the model is less sensitive to the spatial resolution at large scale. And we can see this when we compare the results of the Bay of Seine, represented by the circles, and what we see inside the offshore wind farm and in the buffer zone. In all the indicators, we have less difference between the published model and the tested spatial resolutions when we look to the results at the scale of the Bay of Seine. For our second question, how to deal with reduced spatial resolutions. So for this, we tested a scenario when you close fishing inside the offshore wind farm. And we tried to calculate the relative effect of a fishery closure just by calculating the ratio between the fishery closure scenario and the reference scenario, as you see here with the two maps. And we did this for all the spatial resolutions, and we tried to see what's happening inside each region, and we calculated all the indicators, trophic level, biomass, and catch indicators. And here we summarized the results in this type of plots. So here we have the effect of the fishery closure for different indicators. And for example, the black points, they represent the effect of fishery when we simulated the spatial resolutions of 0.03 degree. And we tried to compare this with the original model represented with the pink points. So the first result is that some indicators like catch and biomass indicators could help us to detect the effect of a fishery closure. However, the trophic level based indicators, they seem very stable, and they are not very sensitive to the fishery closure inside the Bay of Seine. But the most interesting result here is the fact that the difference between the original model and the tested model is not important. As you see here, the difference is less than 1% between both models. So we tried to do the same thing to compare the different spatial resolutions, again, at the scale of the Bay of Seine. And what we see, we have the same patterns, even for the lowest resolutions, which is 0.09. When we multiply the size of the cell by 6, we still have a difference which is less than 2% between the original model and this resolution. So since the results look interesting, so we try to see if we still have the same pattern when we look at small scale, for the offshore, inside the offshore wind farm, and for the buffer zone. And here we found a different result just because we stopped fishing inside the wind farm. So it's normal that we see more effect inside the offshore wind farm. However, if we compare the original model, the one that we published, with the tested scenarios represented by the black points, we don't see a huge difference between both models. And it's even here when we use the lowest spatial resolutions inside the offshore wind farm, the difference is less than 5%. So if you would like to answer our questions, how to deal with reduced spatial resolutions, we can say that EcoSpace outputs seem to be less sensitive to the choice of the spatial resolutions when we compare a scenario to our scenario to a reference scenario. So this is what we recommend in case when we don't have spatial data at high resolutions. Et voilà. Thank you for your attention.
Is it working? Yeah. Ghassan, nice work. Thank you so much. We should do this kind of exercises more. Just being curious, how did you implement the non-fishing? Did you use MPAs or habitat fisheries?
Yes, MPA, yes.
Yeah, the MPAs have, of course, an habitat problem is that you cannot partially close the cell from fishing. It's off or on. So you could also use a non-fished habitat, and then you get much better responses in the catches. You understand what I mean? Because in the MPA, in the whole cell is closed or not, but if you have a very fine resolution, you get massive MPAs. MPAs overrepresent the close the whole cell. You cannot have a partial closure, if you understand what I mean. So if you use the habitat fishing instead, you get better responses in the catches.
Okay, when you say better responses, what does it mean?
You reduce fishing effort proportionally better in different, across different resolutions.
Okay. Well, thank you. I didn't know this before.
In those different changes of resolution, did you adjust the proportion down for the larger resolution in those larger cells? So for example, in high resolution, you'd have, an offshore wind maybe as a 100%, but then in a larger cell, maybe now it occupies 50%. Was it then adjusted down to 50% of that cell, or is it still 100%?
No, we didn't. I think the problem when we change the resolutions, it's not easy to keep the same proportions of the different habitats or the size, for example, of the offshore wind farms. And that's why, if you saw in previous slides, that for the majority of the indicators are decreasing, the biomass and catch indicators, because for some habitats, they decreased a lot in comparison to others. So the biomass of the species related to this habitat decreased and affects the final results.
Yeah, that makes sense. Yeah. And this is very useful. Thank you.
Yeah.
Thank you, Ghassan. And contrary to Jeroen, I'm going to ask you a question.
That's a new one for you.
That's a new one for me, yeah. It's very interesting findings you have here. And when you're working with spillover, the flip side of that coin is dispersal rate. Have you considered doing similar analysis for dispersal rates?
Well, we didn't. This work was done for a master degree student in 6 months, but we are planning. But we are planning to test the sensitivity of different variables in EcoSpace to see how it's impacted with at different spatial resolutions, and also the dispersal rate, because it's one of the most important parameters in EcoSpace Yeah.
So that was a very interesting talk. Thank you. You were looking at ecosystem level indicators. Did you also look at individual species and functional groups to see if there's some differences there, that maybe there were some things that would have popped out but kind of got washed away because, oh, I've got a big biomass group that didn't change much?
Yeah, good questions. We used, let's say, since we didn't have a lot of time and we had a lot of results, I'm not showing all the ecosystem indicators. We decided just to keep ecosystem indicators because because it's not easy for us to look to all indicators at the species levels for problem of time, but it will be interesting to dive more into the details. I agree.
All right, if no one wants to ask, I want to ask you, have you ever assessed the cost of going higher resolution? So usually higher resolution, the limitation is not our computational time, it's the amount of the data we have. You know, the money we spend collecting data can hire $100 modelers, I guess. So yeah, so have you assessed that, or in this project it's beyond the scope?
No, I think we considered that the original model, the one that we published, it was the one with the highest resolution, so we can do better than this. It was the most, let's say, the cost of this model was so expensive. So we try to see what is happening if we try to reduce. And then, as I showed in the last slide, if we used, for example, models with the lowest resolutions, and if we compared the scenarios to our to the reference scenarios, the results will keep the same, let's say, findings at the end. So thank you. Thank you.
So no voting on the advisor of students. All right, our next presentation is Holden Harris, Making, Linking, and Testing Spatial, Temporal, Environmental Drivers in Ecospace, a case study with the US Gulf of Mexico ecosystem model. Go ahead.
All right, thank you. You can hear me, Sheila? My co-authors in this research are Dave Shigaris from the University of Florida and Skylar Sagaris from the NOAA Southeast Fisheries Science Center. I'm Holden Harris, an assistant scientist with the University of Miami, an affiliate with the NOAA Southeast Fisheries Science Center. And then starting July, I'll be transitioning to a new job at the Southeast Fisheries Science Center. My job in this work is part of this much bigger, broader initiative that Howard pointed out at the beginning of the first day, called the NOAA Climate Ecosystem Fisheries Initiative. It's a big program funded from Congress. The idea is to deliver ecosystem and climate information to decision makers. And the framework that they've set up for this is developing these regional ocean modeler teams, developing ways to get this information to regional decision support teams and ecosystem models. And then somehow we'll figure it out of how to make those then operational to inform decision makers. One of the flagship projects for this is this GOLM project that we've called, of taking this high resolution ocean model, using this to inform a US Gulf-wide ecospace model that I'll talk about, and then using that to identify winners and losers, identify potential species and fisheries of concerns, and to simulate future management mitigation scenarios under different climate and fishing scenarios. And I want to acknowledge that this builds on about a decade of work from a lot of others. And here's the papers for this. It was led by Skylar Sagaris, Igel Berenstein, Dave Shigaris. They've developed this robust Ecopath with EcoSim model, and then the current iteration is developing this into Ecospace. So the model that underlies it is an Ecopath model. Has 78 functional groups and 16 fishing fleets in it. It runs 36 years. It's relatively robust. It's fit with 160 time series from fisheries dependent and fisheries independent data. And the work recently is to develop this into an ecospace model. This covers the U.S. federally managed waters of the Gulf of Mexico, has 7 habitat layers, goes out to 400 meters in depth. And the grid cell here is 8 seconds or 14 kilometers squared. For this talk, what I really want to talk about is some of the methods and workflows, because probably this is the only audience that I can present this to that will care about this. I'm pretty excited about it. I think there's some maybe novel ways that myself and my co-authors have thought through and developed that could be applicable to other ecosystem modelers. And I want to share those out. And then we'll zoom back out and talk about some of the applications and implications for ultimate goal of climate ecosystem and fisheries. So this first method that I want to briefly talk about is dispersal rates. So in ecospace, these define the speed that your functional groups move in that 2-dimensional grid that's running ecosim. And so this defines how fast they can avoid poor environmental conditions or find prey or find better environmental conditions. And oftentimes this uses the 300, 30, and 3 heuristic. And the objective is to think about maybe a way of empirically informing these parameters in ecospace. And so I think Dave was the original one that developed this, or maybe this was others, but we developed this technique, and I'll go through these at a high level, but I'm happy to share this out, which explains the steps, and then also the links to the GitHub, which has a lot more information in the code where necessary. But here for this dispersal rates, we can query to get these biological parameters from fish space for total length and caudal aspect ratio, so how fat or skinny the tail is, and swimming mode. And then the code here can query, you put your species list in, you get all the information out, and then you run this log linear function to estimate the relative swimming speed, and then we can scale that to known dispersal rates. And from there, we get this list of dispersal rates, and I'll share this. This is how you copy this into ecospace. The end result is basically that it seems to work pretty well. The species that should be moving fast, like tunas and billfish, have really high dispersal rates. Benthic and small reef demersal fish have low dispersal rates, and it seems to actually do pretty well with that 300, 30, and 3 rule, which I think is a neat way. The second workflow that I want to touch on at a high level is kind of a different way of parameterizing these environmental response functions. So this is information that's available on Aquamaps, which is hugely helpful. And the objective here is we have a workflow that downloads these parameters based on feeding it the whole species list. And then something that's slightly different is I make continuous functions. Typically, these HSPN files are these trapezoidal shapes. So you have your absolute maximum and minimum, and then represented in red here. And here you have these preferred minimums and maximums. And usually you just draw this trapezoid in between it. The code here, if you're interested, queries fish space for these information, and you aggregate these by functional groups, and you review, and we reviewed and adjusted some of these based on expert opinion. This is something that's slightly different. So rather than making that trapezoidal group, I just applied this double logistic function. And the results are then slightly different. Rather than trapezoid, it makes these continuous functions here. And this shows some examples. So these red lines, again, show the absolute maximum and minimum, and the blue lines showed preferred minimum and maximum. And the shapes then are slightly different than trapezoids, which I think might be more biologically reasonable. And this shows how you, this creates a matrix, and this shows how you copy this into Ecospace if you haven't done that. The third workflow I want to share, this took a lot of time, so I'm really interested in explaining this to you guys, is making these spatial temporal environmental drivers. So, of course, this is for these climate, ecosystem, fisheries, and interactions. I didn't even try to do these videos, but these, would have shown videos here. But the end result basically is these are maps that go into Ecospace. I'll touch a little bit more about this. What we're doing is we're leveraging data sources from MODIS satellite data imagery in 2 different ocean models, the MOM6 global ocean model and the HICOM ocean model for the Gulf of Mexico. Maybe one of them did play. All right. Maybe they are playing. Look at this. Anyways, this gives you an idea of what these data then look like. There are a lot of maps basically that then go into the spatial temporal framework. And this is the workflow here, which takes a long time, but I'll be happy to show it to you. And all the code is here, which is cool. But basically, you query the data and you convert it to raster bricks. And then what you do here is the code will match the spatial resolution of your base map file. It can interpolate any missing maps, and then it outputs these into the ASCII files for what you feed into Ecospace. And they also have some code here for making these maps as well. And this is the spatial temporal framework. Of course, there's a whole workshop on this later this week. So if you're interested, please attend that. But this is what this looks like, and this is how you copy and link these into Ecospace. So now that we have these, done a lot of work to make these spatial temporal drivers, we want to compare the outputs in Ecospace. And what I've done is develop a workflow that then helps augment what's already done in Ecospace to compare that. So here's one example. So we have 3 different scenarios here of how we drive primary production. The videos work. So we have the Modus chlorophyll A, we have the MOM6 ocean model of chlorophyll A, and the MOM6 vertically integrated. And here's the Ecospace results here on the right. And so you see a lot of movement. It's hard to, differentiate what's going on, but it looks like things are different. And so what I did is develop a workflow to compare Ecospace to your observed output, Ecospace to your Ecosim output with visual plots and then metrics of fit. And so what you do is you set up your output directories here, and then you can run this code that's available here at the GitHub here. And you can set your input files to match accordingly. And then what this does, it reads in the Ecosim, reads in the Ecospace time series files. You have to do some processing so that it all works out. But then you can plot the biomasses and then also do the air metrics as well. And so this shows some examples here. So our black dots here are observed data that are read in from our reference time series. In green, these are the Ecosim projections over the same period. And then the different colors show the different Ecospace scenarios. And so these show by functional group, so it's a little easier to tell and diagnose what's going on per functional group. Again, this is done after you run Ecospace. You just run these in R. And then the last step is to calculate an objective function. So similar to how Ecosim calculates metrics with sum of squares, we have a couple of different metrics here, and you can use it weighting or non-weighting or root mean or root squared weighting. And then it calculates these metrics by functional groups, and then we can aggregate it together. And one finding that I've seen is that the Ecospace fits are actually relatively similar to the Ecosim fits, which is actually fitted in Ecosim, which is nice. So we got really into the weeds. Let's zoom back out to the summary and kind of the broader meaning here. So this is the workflow here. We're taking these ocean model outputs, running it through the spatial temporal framework. These are linked partly with these environmental preference functions with this continuous function setup. You run the simulations in Ecospace, and then you compare the output spatially, which I didn't go into, temporally, and then also kind of objectively with your fits. And this is where we're going. Thank you. Again, the idea is to leverage the work that's being done with this the NOAA CEFI program. They're making these really high resolution downscaled ocean models. This is for the Northwest Atlantic, but they'll be throughout the United States area. And then we're going to link these into Ecospace. So that's the current and next work. Currently, we're skill testing the hindcasted, the observed data, which I showed you a little bit about. The upcoming work is to do this with future projections to identify the winners and losers and species of concerns and to simulate management scenarios. And we have a student starting that'll be working with Dave Shigeris here. And then through CEFI, we're also going to have a handful of positions for fisheries oceanographers and ecosystem modelers. So for PhD students and current postdocs, we have a couple of different positions and levels opening up. So if you're interested, please come talk to me. So the takeaways, please come talk to me at this conference. if you're interested in any of these, empirically estimated dispersal rates, continuous environmental preference functions, making ecospace spatial temporal environmental drivers to use in the spatial temporal framework from ocean model outputs or satellite imagery, and then workflows to plot and compare those in ecospace. I'd love to talk to you guys about that. I'd also love input from people that have done this actually, before, of operationalizing these results into management, of picking winners and losers. I'd love to hear inputs. And then final ping. And again, I think it's exciting work if you're interested in full-time in a job along these. Yeah, we're looking for people. So thank you.
Time for questions.
Yeah, great talk. Thank you. And we have gone through a lot of these, not trying to optimize our workflow. So it's a great example. I was wondering for the response functions. You said that you weigh them, but how do you weigh them by functional group? What kind of is it the biomass you use? Is it the consumption to get the response function of the functional group?
To make those environmental preference curves there, those aren't weighted. Those are just from the parameters from provided by Aquamaps, the absolute minimum, the absolute maximum.
But to put them in the model, you have groups, functional groups that have different species. So somehow you have to weigh them to have.
Yeah, and in these fits, we do different weighting. So right now I'm just using the EcoSim fits, or the weights that are in EcoSim. And then I do compare the fits with weight, without weights, and then also take the square root of the weight too.
I'll come to talk to you.
Okay.
Thank you.
I think kind of this year.
Okay.
Excellent presentation, Holden. It's Greg Oldford here. Marta asked my question, so I thought just really impressive work. Also pursuing the same kind of. I had to tackle the very similar thing, moving between different types of models and just processing data. Yeah, and I guess kudos for getting the GIFs to work in the PowerPoint. That's really amazing.
Nice. Hey, this is good work. I'm so happy to see somebody else geeking out. It's good. No, really. And this is basically what we try to do with Ecopath, with EcoSim. We could overload it with statistical tools, with plotting tools, but the idea for us is to provide you with the means to put the inputs, pull the data out, plot it your own way. We are establishing an Ecopath with EcoSim GitHub repository where we want to share scripts, because it's just ridiculous if we keep reinventing wheels ourselves. So let's bring that discussion forth as well. But thanks for this. It's cool.
Yeah, that might be a lot more nimble too, to be able to just do this in a GitHub and have multiple people.
And then just reuse script, build them.
Yeah.
Nice. Good.
Yeah. They said all the nice things. I don't need to do that. But it is nice. We have a Shiny app for estimating dispersal based on individual behavior. So it'd be interesting to include that into your comparison of how things work. So that's one thing we can talk about. Yeah. And also, I just noticed that on your fits, your EcoSim fits, you fitted very nicely to the catch for the first year, and then it was diverging. And often what we do is just to change that for the first year and get a much better fit overall. So there's some things on that fit that really will be interesting to see how we can improve those.
Yeah.
That's nice work.
Thank you, Bill.
We're out of time for questions, so go to the Holden and then top
Yeah, thank you.
All right. Great on time, I think, but let's go on to the next presentation by Stefan Koenigstein, an ecospace model for the Northern Humboldt Current ecosystem, dynamically driven by regional ocean projections. Go ahead, Stefan.
Hi, everyone. Yeah, I'm Stefan Königstein. I'm a postdoc at ZMT, Leibniz Center for Marine Tropical Research in Bremen, Germany. And actually started working with Ecopath very recently, a few months ago. Though I realized I was at Ecopath 30 years. So it's really nice to see you faces again, but I worked on mice models mainly in the meantime. And this is work for the Northern Humboldt Current, the Peruvian upwelling system, which we're doing together with the Peruvian National Institute for the Sea. So the Northern Humboldt Current system is an upwelling, eastern boundary upwelling system, which means it's highly productive, it's highly variable, and very also spatially heterogeneous. You're probably aware that Peruvian anchoveta is one of the biggest single species fisheries in the world. And in these kind of upwelling ecosystems, forage fish like anchoveta are very important in transferring biomass to the higher trophic levels, and they exhibit typical boom-bust cycles also. So it's a really nice case study region to try to link the environment to fluctuations in the ecosystem and in fish stocks and fisheries. A little bit more detail on that, on the environmental detail. You have the cool, nutrient-rich waters being upwelled to the surface, and they kind of drive the ecosystem, drive the productivity in lower trophic levels. The higher trophic levels obviously rely on that energy, but they're also driven by physical factors, environmental factors like temperature and oxygen, which kind of, as we know, physiologically influence growth, reproduction, mortality, early life stage mortalities, these kind of things. And then also the oxygen minimum zone. There's an area which is very, very poor in oxygen, especially in the Peruvian system. It's pretty shallow, and so that limits also the habitat for higher trophic levels, leading to basically distinct ecosystem above and below the oxygen minimum zone, or above and below the oxycline. So I'm working with a model that has been developed before for the Peruvian system. Basically my guiding question is, how do we reduce that spatial temporal complexity into something that is able to drive the food web? So we've been updating biomass and diet data for the existing Ecopath and Ecosim models, and in the process of calibrating it to a survey time series for the Ecosim model. And here we use the ocean biogeochemical model to force the two phytoplankton and two zooplankton compartments. And there's another one, there's macrozooplankton, which then basically we keep in the ecospace model. You can see here the middle trophic levels, small pelagics and other pelagic fishes are really important in the food web. And I think it's about 40 species that are in the 40 compartments in the model. And some of them are resolved into different life stages. So here's the ocean biogeochemical model that we're using, developed at EMAPE with partners at Ifremer in France. So it's a Cocopiscis model, and it's a regional downscaled model, hindcast over the last about 3 decades, and it's 1/12 of a degree resolution. We're kind of simplifying it into 4 depth levels for the input to ecospace. And we've been reducing the resolution to 1/2 a degree for first, just to have a fast running model for calibration, planning to increase that later. And we're using currently the approach to use all plankton biomass integrated over the upper 200 meters of depth. And yeah, you can see here the drivers, the initial driver set that we picked. So the plankton compartments, as I said, are integrated over the whole depth. For temperature and oxygen, we integrate over the mixed layer that's above the oxycline, basically. But we also have deeper layers as input for other species. That's oxycline depth. Yeah, so that's basically the initial set. Then we're looking at interannual variation to kind of help us in calibrating the model. We're doing that for 6 different regions, divided in north, south, and center, and coastal and offshore. This is just an example for SST where you can see the cool temperatures linked to upwelling. So here is the distribution for temperature and oxygen. I'm just giving an example for an El Nino year. So the warm year with low upwelling and a La Nina year with stronger upwelling. So you can see the temperature signal here. So one interesting thing that happened is if we integrate over the mixed layer, we're kind of filtering out that upwelling signal. So we basically have a stronger north-south gradient, especially in temperature. And oxygen is a little bit like that, but not as much. We still have the oxygen depleted areas here under stronger upwelling situations. Then we're looking, as I said, at internal variability, and you can see that the hindcast is really nice at reproducing. There was a really strong El Nino in 97, 98, and you can see the high temperatures here, kind of across the whole region. You can see the increased temperatures also here. That signal is much stronger in the core upwelling region and the central coast, and you can see the very shallow oxycline here in that region, which is also changing with upwelling strength. So one important to say, that's actually a typo. So temperature and oxygen are positively correlated here. Very revealing typo, because it's kind of opposite to what you expect in many other regions of the world oceans, especially at the surface. Due to upwelling, the correlation here is positive. So you have under El Nino situations, for example, you have higher temperatures and more oxygen. Yeah, so the way we're integrating that into Ecospace is very similar to just what Holden just showed in the previous talk. We're aiming to do that as mechanistically as possible. So we're trying to use physiological or experimental data and actually inform the optimum temperature and the minimum maximum for temperature. And at the moment, I'm just playing around with oxygen, kind of a sigmoidal function, basically just an oxygen limit, where this temperature curve would then be constrained to its internally in Ecospace it's multiplicated. Though due to the correlations we have here in the upwelling system, the constraining is more on the lower part of the temperature curve. Yeah. So for plankton, there's also very typical distributions. The top ones are the bigger compartments, the mesozooplankton, sorry, and the larger phytoplankton, the diatoms. And these have the higher biomass. The scales here are different. I just wanted to show the distribution a bit better. So the diatoms are really driven by the nutrients in the core upwelling area. The mesozooplankton is similar, but it's a little bit more offshore. And the nanophytoplankton and macrozooplankton kind of dominate the more offshore areas. Overall lower in biomass and differently distributed. In the internal variation, don't bother looking at all the details, but the main story is that is also this plankton biomass internally is varying the same way with upwelling strength. And there's a gradient between offshore and coastal, as you can see, for example, here, as I showed before on the spatial distribution. And currently what we're doing is we're forcing all the plankton groups, or the 4 plankton groups I mentioned in Ecospace. It might actually be equivalent to only forcing the phytoplankton, but the results were better so far. And the reason why that could be equivalent is basically they're highly correlated. So this just shows the 2 small groups, the small phytoplankton and the small zooplankton. And here's the larger zooplankton and this larger phytoplankton. They're positively correlated. And this is probably linked to just the way the biogeochemical models work. It's basically a transport of nutrients or biomass, just as in Ecopath. So they kind of, you have this correlation, they feed on each other. Zooplankton feeds on the respective phytoplankton compartment. And this also leads to a link with temperature, which is something that we're trying to think about when we're fitting the model, that in some areas, especially further offshore, temperature is inversely correlated to the main biomass compartment diatoms and some of the other also. So the way I'm thinking about this is really like this 2, probably classically a traditional view of an upwelling system. You have these 2 trophic pathways. One is the large items, basically upwelling driven, and one is the one that is more offshore, more under low upwelling conditions with a smaller phytoplankton and smaller zooplankton compartments. And this is just one of the initial screenshot, at least wanted to show something from Ecospace. So this is how we going ahead, fitting anchoveta distribution. It actually works pretty nicely that it's constraining it to the coast due to the feeding on diatoms. Then the north-south distribution, fitting that a little bit, that's still in progress. Should be constrained a bit more in the north probably. And then one thing, for example, if we have this very high biomass fluctuations, one thing that happens here is that under 10 times the amount of biomass, they're just spread out everywhere, which is not what we're observing. But we're still in the process of fitting distribution versus biomass and the feedbacks, changing the environment response, dispersal rates, vulnerabilities, and so on. Yeah, that's it. As conclusions, I think the regional, looking at the regional covariation and in the drivers really helped us to develop a fitting strategy, but we're still busy at it. And it's been worked much better to use temperature and oxygen over the mixed layer. And together plankton distribution works to fit the distribution and the pelagic species. And yeah, we're also planning on using fitting routines using external tools, as we've seen in the previous talk. So I'm definitely up to chat. That would be very interesting for us to do that. And at the moment, we're going ahead in a way that we are fitting interannual variability and keeping seasonality for later, but it's another important factor because the upwelling system has obviously the distinct seasonal upwelling pattern and also seasonal migrations in some of the species. And then the further plans in the project are to project the ecosystem into the under under different emission scenarios, and then project impacts on different fishing fleets and do a participatory assessment of adaptation strategies, working together with stakeholders in workshop settings to look at adaptation options for different user groups. Yep, that's it. Thank you very much.
We have time for questions.
Thanks. It's a really nice presentation. More a comment, just depending on where you go to with the research project. In that, I don't know if you heard yesterday the conversations about utilizing stable isotopes and trying to incorporate that into Ecopath models. For your area, for your region, there's a lot of nice, interesting data that's came out quite recently, and the guy who's led a lot of that work's actually moving to Glasgow later this year. So if you're wanting to connect and look at the data that he has, particularly for the coastal system and stuff, then we can try and make that happen if you want.
Yeah, that sounds amazing. It's a great idea. Thanks, Bernd. Yeah, fitting the diets was one major thing that we still, I think there's still uncertainty in it.
Yeah, my question was really about a little bit about the fitting that you have of your lower trophic level model. I don't know how much data do you have to actually, because some of those positive correlations you had between, you know, diatoms and zooplankton seems very odd to me as a food web person. So do you have any data to kind of validate those predictions from the models, or?
So I still have to look into actual survey data. We do have some survey data. I don't have them in spatial resolution yet, but I'll look into it. So the way biogeochemical models are usually calibrated is looking at nutrients, right?
Yeah.
Looking at nitrogen.
Yeah.
It's probably a simplified picture of what's going on.
Yeah. And I don't know in these models whether they have the actual, you know, food web connections between those things, or if it's just nutrients flowing up. And then if that's the case, if I was doing this, I would actually not use those maybe use phytoplankton and micro and nano zooplankton, but not the higher trophic ones to link them with your ecospace model, because if they're not getting the food web situation correct in their lower trophic level models, then, you know, you're already starting from a bad position from a food web perspective.
Yeah, I agree. So that my first thought also was just to force the phytoplankton. I guess you're just moving up the tricky part up the food web if you force the other ones also. And the problem is that in the biogeochemical model, you basically have a quadratic mortality for zooplankton, and that's kind of a simplified thing.
Yeah, so I wouldn't do that.
Yeah. But that being said, I think they're pretty good at kind of recreating the spatial distribution.
Yeah.
Maybe more so than the biomass.
Yeah.
Great. Thank you, Steve.
Thank you.
I'm just going to announce the coffee break. So we have a coffee break until Sheila rings the bell. That's how it works, right?
Coffee break. For the coffee break. I think you guys are awesome at keeping to time. Before the coffee break, the three VLIS people who got money from VLIS, if you can come forward, it is, remind me, Eduardo, Letitia, and Larusha. Please come here first before you have coffee, because we have to have a photo opportunity with VLIS. That's the least you can do, is get your photo taken. The rest of you can go, and we should be back, if I'm not mistaken, at 11:30. 11:30. So enjoy the coffee.
Yeah, it's also, it like rolls up and it smells as it's traveling. Six. Yeah.